All right, well, it's good to be with you this evening, and I do get to talk about the James Webb Space Telescope, this marvelous new instrument that we have, paid for by your tax dollars. So thank you very much for your contribution to this instrument. It's helping to confirm creation, and so that's a great use of tax dollars. So that's what it looks like. That's the James Webb Space Telescope. So it is out in space. It's a million miles out in space, and taking these wonderful images of very distant galaxies. And I want to bring some of those results to you tonight and how they confirm creation, as well as some brand new research. You'll be the first group to hear it. Other than there's a group of students I spoke to up in Washington State. They heard it a little bit before you, but you'll be the second group to hear it. Brand new research that's about to be published. It's been peer reviewed, so I feel okay talking about it now. And I want to begin by talking about the history of this spacecraft and its predecessor, the Hubble Space Telescope, because most people are familiar with the Hubble Space Telescope and some of the remarkable images that it's delivered. You can Google any image in astronomy and you'll get the best ones are Hubble, right? So that's the Hubble, and that was launched back in 1990. The James Webb was being planned even before that as the successor to Hubble, and it is a successor to Hubble in many ways, but it's different from Hubble, and I want to show you some of the differences and similarities between the two spacecraft. So the Hubble Space Telescope has a mirror that is 2.4 meters in size, so would that be 7 foot 10 inches? So that's the diameter of the mirror. But the main advantage of it is it's in space, and so that gives it a very clear view of the universe. There are ground-based telescopes that have mirrors that are much bigger than Hubble, and in astronomy, bigger mirror, better view, right? You get more light gathering power, fainter objects look brighter, and you get more resolving power. You can see stars that are very close together instead of blurring together. With a bigger telescope, you can separate them as individual stars. So that's Hubble, named after Edwin Hubble, the astronomer who discovered that galaxies are redshifted, that they're moving away from each other and from us. He discovered that back in the 1920s, and so the telescope's named after him. The Hubble Space Telescope is in low Earth orbit, so it orbits just around the Earth. It doesn't go anywhere. It just orbits the Earth. And that is an advantage because it makes the telescope accessible. And so Hubble is upgradable. And it's been upgraded many times. The original instruments, the mirror's the same, but the original instruments have all been swapped out, replaced with newer ones. So that's pretty neat. It's powered by a 486 processor, not even a Pentium, because by the time they test these things, the next chip's already come out, but they haven't tested that one yet. So it's kind of amazing what it can do. So pretty neat. And because it's in low Earth orbit, it's accessible. The astronauts can swap out the instruments, and that's what allowed them to correct the mistake. Remember when the Hubble was first launched and it had a problem with the mirror? It's a minute curvature problem that was due to the instrument they used to test and correct curvature. And it caused it to be a little bit off, which caused the first images to be blurry, and that was so embarrassing. But then they basically gave Hubble glasses. They put CoStar in, which gave it a contact lens, basically. And the newer instruments are designed to deal with the flawed curvature, so you get crystal clear images with it. And what a spacecraft it is. And it's still in operation. It'll work concurrently with James Webb for a number of years anyway. And Hubble sees what you see. Hubble has the same wavelength range as human vision and a little bit more. So it can see the rainbow, and it can see a little bit beyond the rainbow. It can see a little bit into the infrared and a little bit into the ultraviolet, but more or less it sees what you see, which is kind of neat. That doesn't necessarily mean that the images are true color. Some of the images that Hubble takes are what they call false color, like this beautiful image of the center of the Eagle Nebula, which I call the Pillars of Creation, and it is stunningly beautiful. The Eagle Nebula is actually red. This is a false color image because there are multiple filters that they use to take these images, and they don't have to combine them in the same way that we would perceive. Often they do, but they don't have to. Sometimes they're not trying to fool anybody. Sometimes people think, well, they're making these false color to fool us. No, they're trying to do science, and that's just the way they can pick out certain features. So some of them are false color, but a lot of them are true color. They're a good approximation of what you would see. This is a Hubble image of Saturn, and that's pretty much what you could see if you had eyes that were that big and could zoom in like the Bionic Man and could zoom in on Saturn. So there you go. So that's what it looks like. And it's just so beautiful and crystal clear because it's above Earth's atmosphere. Ground-based telescopes can see fainter objects than the Hubble if they have a bigger mirror, but they cannot see as crisp as Hubble because it's above Earth's atmosphere. And so images like this of the Whirlpool Galaxy, we didn't have I mean, we had images of the Whirlpool Galaxy before 1990, but any textbook you see of the Whirlpool, it'll be just a little bit blurry because it was taken by an instrument that's on Earth, and it had to look through Earth's atmosphere, and Earth's atmosphere creates a little bit of a blurring effect. With the Hubble, it's just crystal clear because there's no blurring in space. It's always frustrating for me as an astronomer. That light travels from that galaxy, it's 30 million light years in space, hundreds of trillions of miles, only to be blurred in the last 5, right? As it enters the Earth's atmosphere. But the Hubble's above all that, and so it can get these crystal clear images. And that's one of the things that makes it just superior to ground-based telescopes in many ways. In the mid-1990s, they pointed the Hubble at a small section near the Big Dipper in an area of our galaxy that's relatively empty of stars because we wanted to see what's beyond. That's what's beyond. And it's amazing. It's amazing. And I remember when this came out. This is the Hubble Deep Field. And when it came out, I was amazed at it. To me, it just made me want to worship God, who spoke all those galaxies. What you're seeing there are galaxies, right? Each one of those little specks, that's not a star. That's a galaxy with maybe 100 billion stars. Some more, some less. But in any case, at incredible distances. And it goes out to a redshift of about 6. Galaxies are redshifted. Their light is being stretched to longer wavelengths, and the farther out they are, the more their light's been stretched. I'll come back and talk about why that is. But suffice it to say, a redshift of 6 means their light's been stretched out like 6 times beyond regular. So that's impressive. And that corresponds to a distance of about 12.8 billion light years. There's different ways of measuring distance in space. There's at least 5 different ways when you talk about cosmological distances, and that has to do with the expansion of the universe. How do you describe a distance between 2 things when that distance is constantly increasing? How do you do that? There's about 5 different ways to do it, and they're all relevant, but this would be the one that would be most analogous to the light travel time in the secular view. So they would say we're seeing these galaxies not as they are, but as they were 12.8 billion years ago. Now, I have an issue with that because I don't believe in the billions of years. But nonetheless, I get where they're coming from. And in their view, this is a billion years after the Big Bang, because the Big Bang's supposed to happen 13.8 billion years ago. But you're seeing galaxies that go out almost back in time to the point of the Big Bang, right? So keep that in mind. In the secular view, when you look out further into space, it's like looking back in time. I would say that's not exactly true. There's ways to see the universe in real time. I've written about that. Maybe you've read some of my articles on that. But in any case, what was amazing is that you have galaxies less than 1 billion years after the Big Bang, because it's supposed to take galaxies time to form. And so this was a bit surprising to my secular colleagues that they were hoping at least we'll see. They thought, well, as you go back in time, you'll see fewer and fewer galaxies, and eventually there won't be any because you're looking back to a time where they haven't formed yet. That makes sense in the secular view. And so it was surprising to see not only galaxies, but that many galaxies at those distances. Really quite impressive. And so that was a bit surprising. Furthermore, the galaxies that we see, they were expecting to see baby galaxies because galaxies, when they first form, they ought to be small and clumpy because it takes time for the stars to collect and form into a galaxy. And then they're supposed to grow bigger with time. And through collisions, they eventually get organized and become these beautiful spiral and elliptical galaxies that we see nearby. So it's surprising that you see spiral and elliptical galaxies far away and not the baby galaxies that were expected. And so the expectation was, well, they must have formed beyond that distance. The first galaxies must have formed even at greater distances. So they went out deeper into space with the Hubble. This is the Hubble Ultra Deep Field. And they found more galaxies. So this goes out to a redshift of 8.3. So that corresponds to 13.1 billion light years, 700 million years after the supposed Big Bang. You're still not seeing the baby galaxies. You're still seeing fully designed galaxies, almost as if they were just spoken into existence by God. How about that? But it turns out that even though there are still galaxies at that distance, and the secular assumption is that the first galaxies must have formed even farther out and therefore farther back in time. but there is a problem because the Hubble can't go out much further than that in terms of its ability to see distant galaxies. And it's not a matter of light gathering power. It has to do with the redshifts. So Edwin Hubble, back in the 1920s, discovered that there is a relationship between a galaxy's redshift, which he interpreted as a Doppler effect. He thought these galaxies are redshifted because they're moving away from us. It's a perfectly respectable assumption. And he found that the farther away a galaxy is, the faster it's moving away from us. And that we call that the Hubble law in honor of Edwin Hubble, who published this result in 1929. So you can see that statistically, I mean, there's some variance, but statistically, the farther away a galaxy is, the more redshift it is, the faster it's moving away from us. And if you picture what that would look like, that would mean all the galaxies are kind of moving away from all the other galaxies. Everywhere is getting bigger. It's as if the universe is getting bigger or being expanded. We might have anticipated that. There's some scriptures that seem to suggest that. But in any case, it was discovered by scientific means in 1929. Now, that doesn't necessarily mean that galaxies that are farther out look redder. Sometimes people expect that. You'd see two galaxies and they're both kind of whitish. One might be twice as far away as the other. It might be twice as redshifted. It doesn't necessarily look red. Why? Because a galaxy gives off multiple wavelengths of light, some of which we can see, some of which are beyond our ability to see. Now, when that galaxy's light is redshifted, the light we can see gets redshifted out to where we can't see it, but other light that the galaxy emits that's ultraviolet, that's beyond our ability to see this way, gets shifted into our ability to see. And so the overall color really doesn't change very much for relatively nearby galaxies, but there's a limit to that effect. For faraway galaxies, they do start to look redder because galaxies don't emit all wavelengths equally. At a certain point, they taper off. And that limit's called the Lyman limit. It happens at a wavelength of 911 angstroms. Light that has a wavelength shorter than 911.3 angstroms will be absorbed by hydrogen gas in the galaxy because it has the right energy to ionize the hydrogen atoms. Okay? And so basically what that means is galaxies are opaque in frequencies of light with wavelengths shorter than 911 angstroms. So they don't emit equally over all ranges. At a certain point, they stop emitting and they're black beyond that. Now what that means is, as the galaxy is redshifted, the point at which it stops emitting light gets redshifted and redshifted and redshifted, and eventually it gets below Hubble's ability to see. And so those galaxies that are at a distance farther than that, Hubble cannot see them. They are invisible to Hubble. Okay, and so that's why we need a better spacecraft. We need a spacecraft that can see these ultraviolet or these infrared wavelengths of light that are below Hubble's ability to detect. And that'll allow us to see redshifts, galaxies that are at a much farther redshift than what Hubble can detect. And so that's why the James Webb Space Telescope was invented. And it was already being planned in the 1980s, before Hubble even launched. They were already planning its successor. That's the way it works in science. If you want to get stuff done, because especially if you want to go through the federal government, it takes a while, okay? And it takes funding to do that too. So this is an $11 billion spacecraft. So it took a while to do that, but I'm glad they were already planning that. Back when I was in grad school, they were planning it. We were already talking about it. It hadn't been named the James Webb yet. It had been named the Next Generation Space Telescope. That was the successor to Hubble. And I remember back in my instrumentation class, back in, I think it was 98, I was back in my instrumentation class, we were talking about this amazing new spacecraft. And the professor, he'd actually worked on parts of it, and I think he helped design the solar shield that you see there at the bottom, and how it unfolds and so on. So I know people that have worked on parts of it, and that's pretty neat. It was a collaborative effort, a lot of brilliant people working on this to make it happen. But I remember my classmates and I were all excited about this Next Generation Space Telescope, but we were bummed that we'd have to wait till 2007 for it to launch. And of course, it's 2022 that it launched. So things take longer than they do, it would appear. So anyway, in 2002, they renamed the spacecraft in honor of James Webb, who was the director of NASA from 1961 to 1968. And if you know those years, those are the early Apollo years. So James Webb was instrumental in getting a lot of, especially federal funding for the Apollo program. So if you're happy that people walked on the moon, you can thank James Webb. And he was a good guy. He was a moral guy. The LGBT community, they don't like him. They didn't want the spacecraft to be named after him because he would not tolerate sexual perversion in NASA. I'm fairly happy with that, and so I admire the guy. But fortunately, NASA did not take their advice and rename it. They said, no, we're naming it the James Webb. So I'm glad about that. So he passed away in '92. So he didn't really have anything to do with the telescope that bears its name, bears his name. It's just named in honor of him. So here's the mirror on the James Webb, and you can see it's bigger than Hubble's by quite a bit. Hubble again is 2.4 meters. James Webb is 6.5 meters in diameter. That's over 21 feet. That is a big mirror. It's so big that we can't really make, well, we could make a mirror that big, but there's no way we could ever get it on a rocket because none of our rockets have diameters that could fit that in there. And so what they did instead is made 18 smaller hexagonal mirrors that fit together like a jigsaw puzzle. And the outer columns, the outer two columns that you see on the edges fold back, and that allowed them to get it into the largest rockets that we have. So pretty ingenious, pretty ingenious. And of course, designing 18 smaller mirrors means they have to line up exactly. So each one is motorized so that they can line up, and they have to be lined up to within the fraction of a width of an atom. It's just amazing. It's just amazing. And that was done after it launched because, you know, the vibrational launch is going to mess them all up. So it was done. They spent the first month or so calibrating all those mirrors to make sure they're all pointed in the same direction. And it has software to allow it to do that. Brilliant design. The mirrors are made of beryllium, which is a very light metal. My instrumentation instructor swore by beryllium. He just thought it was the best metal. He laments that we don't use it more often, but that's because the vapor of beryllium, if you inhale it, it's fatal. So that's why we don't use it. But he said, but only if only if you breathe the vapors. It's safe to touch. You can lick it. You know, it's perfectly safe otherwise. He swore that beryllium golf clubs would be the bee's knees. But anyway, that's what the mirrors are made of. And so that's a nice light metal. It also has thermal properties that are well understood. Metals contract when they're colder, right? You know that. Beryllium will do that up to a point and then it stops. That's kind of convenient. But even so, when they designed those mirrors, they made them a little bit too large on Earth so that in space, when they're cooled, they would contract to the right size. It just shows you some of the thought that went into this. It's really brilliant. And then the reason they have that yellow tinge is because they are coated with a thin film of gold, about 800 atoms thick. And the reason for that is the James Webb is designed to see infrared. Gold reflects infrared really well. If you want to see visible light, you want to use silver or aluminum. And that's why most of your telescopes that you'd get, you know, from Orion.com or whatever, they have silver or aluminum. But James Webb's covered with gold because that reflects infrared very well. And most of the other differences between Webb and Hubble are due to the fact that it needs to see infrared instead of the visible wavelengths. So this is the frequency range. Again, the frequency range that we can see is relatively small. There's a lot more to the rainbow than that thin thing we see. If we could see all those wavelengths, the rainbow would extend much further. Hubble can see a little bit beyond what we can see, but then James Webb, it's not designed to look at visible light. It's designed to see infrared, and so it goes way down into these wavelengths so that it can see high redshifted galaxies whose light has been completely shifted out of the visible wavelengths and into the infrared. Now, because of that, it needs to operate at very cold temperatures. Because at room temperature, the James Webb Space Telescope would not work. At room temperature, we give off infrared radiation. Maybe you've seen either on television or you've seen those thermal goggles that people put on. Everybody looks like they're glowing. We are glowing in infrared. And so if we could see infrared, we'd turn off all the lights, we'd all be glowing. James Webb, if it were to operate at room temperature, it would be glowing and it would see its own glow and nothing else. So it has to be very cold. It's designed to operate at a temperature below 40 kelvins, 40 degrees above absolute zero. That's negative 370 degrees Fahrenheit. That's the temperature at which it's designed to operate. And then one of its instruments needs to be even colder than that. But the main instruments operate at that temperature, and that's so it doesn't see its own glow. Okay, pretty amazing. And it reduces what's called dark current, which creates artifacts in the instrumentation. So in order to achieve that, they designed a sun shield. That's what that thing, that silvery thing on the bottom is. That's about the size of a tennis court. This is a big spacecraft. And again, you can't get that in any rocket, so it was designed to fold up and then unfold when it's out in space. Pretty ingenious. And each of those layers separates the next layer, and they calculated how much the temperature would drop with each layer. So the bottom side of that always points toward the sun. The telescope is always on the opposite side as the sun. And just by being out in space and having that sun shield, it will naturally cool to 40 kelvins, 40 degrees above absolute zero. That's what that sun shield is for. And if you think about, there's all kinds of stuff that needs to be thought of in order to do that. Because have you thought about what electronics would work at 40 kelvins? Would this computer work at 40 kelvins? I know the battery wouldn't. The battery would be gone, right? But even if you had another power source, what transistors work at, I mean, do we know? I don't even know. So they had to do some experiments to find out what kind of electronics work at those cold temperatures. And so it just gives you a little bit of a feel for the ingenious engineering that went into this spacecraft. So now the James Webb Space Telescope has 4 different imagers on it, 4 different detectors that work in different wavelengths. And 3 of them are designed to operate at 40 kelvins. The remaining one, called MIRI, goes deepest into the infrared, and so it needs to be even colder. It's designed to operate at 7 kelvins, 7 degrees above absolute zero, which is negative 447 degrees Fahrenheit. So it's just, and in order to achieve that, they have an onboard cooler. I don't even know exactly how it works, but it brings the temperature even colder so that that instrument can work. Now, because James Webb has to be so incredibly cold to operate properly so it can see infrared, you can't put it in Earth orbit because Earth is at room temperature on average, right? Some places are hotter, some places are colder, but can you imagine orbiting this giant light bulb? It's not going to work. So unlike Hubble, which is in Earth orbit, they put the James Webb far away. It's 1 million miles out in space. There are 5 locations where the gravity of the sun and the Earth balance such that if you put an object there, it will orbit along with the Earth, orbiting the sun in 1 year, maintaining its configuration with Earth. These are called Lagrangian points. James Webb is at the L2 Lagrangian point, which is beyond the Earth in the opposite direction of the sun, about 1 million miles out in space, and it actually orbits around that Lagrangian point. So it's a non-Keplerian orbit. It's kind of interesting. But they did that to get it away from the Earth, to this massive source of heat and light. And the sun shield always keeps the spacecraft on the opposite, keeps the telescope on the opposite side as the sun. So that's what it looks like. Now remember, one of the advantages of the Hubble, low Earth orbit, something goes wrong, we can go up and fix it. If James Webb, something goes wrong, $11 billion down the drain. Okay, there's no way to fix it because human beings can't, we haven't gone that far out in space. We've only gone as far as the moon, and that's been a while. So, and they talked about, should we build an arm on it so that an unmanned spacecraft can go out and grab onto it and fix it? The expense was too great. And so they said, well, we're just going to have to make sure we get it right the first time. And fortunately, they did. Fortunately, they did. So it's a wonderful spacecraft, and it's operating flawlessly. So what are the predictions? Why build this spacecraft? Well, again, the secularists wanted to see out to a great distance in space. That's commendable, but they think it's like looking back in time. And so the reason they wanted to build this spacecraft is to see the distance at which galaxies have not formed yet. And presumably, at very nearly that distance, you'll start to see very small galaxies, baby galaxies. And then there will be a distance at which there aren't any because you're too close to the Big Bang, not enough time has elapsed. So the secular predictions, 1, fewer galaxies at great distances, because you're looking back in time in their view, and there shouldn't be any beyond a redshift of about 14. Now there's a relationship between distance and redshift, and it's complicated, but redshift is a distance, think of it that way. So you shouldn't see any galaxies beyond a redshift of 14, and there should be relatively few at redshifts approaching that. And the ones that are there, that are approaching that limit, should be low mass, clumpy, irregular baby galaxies. Galaxies that have just collected their first little bit of stars and haven't had time to organize into these beautiful spirals and ellipticals that we see nearby. That's supposed to take time, it's supposed to take mergers and so on. So the earliest galaxies should be low mass, clumpy and irregular, and very few, and then none beyond 14, okay? And then finally, the farthest galaxy should have no heavy elements. In astronomy, a heavy element is anything heavier than lithium. So yeah, on the periodic table, you got hydrogen, helium, lithium. Everything else is a heavy element in astronomy, okay? And there's a reason for that. In the Big Bang view, the Big Bang is supposed to, the universe pops into existence. It's very hot. There's the energy is, the temperature is essentially infinite. And then as it cools, eventually the temperature drops to where atoms can form. And given the density and temperature at that time, the only atoms that should form in the Big Bang are hydrogen, helium, and lithium, the three lightest elements. The Big Bang cannot produce any heavier elements. But we got heavier elements in the universe, right? We're made of a lot of them. We're made of stuff like oxygen and carbon, and we should be grateful for that. But the Big Bang can't produce that. So how do you get the heavy stuff? In the secular view, the first stars form from hydrogen, helium, lithium, and then in their core, the massive stars, the ones that are really massive, in their core, when they run out of hydrogen, they start fusing these other elements, and eventually they explode, and so stars produce the heavier elements, and then when they explode, blow them into space. And so if you've heard Carl Sagan say, we're all made of stardust, or we're all made of star stuff, that's what he means. In the secular view, heavy elements are produced in the cores of stars. Now, that being the case, the first stars that formed, what would they be made of? Only hydrogen, helium, and lithium, because the other stuff hasn't formed yet. Now, when the most massive of those stars explodes and produces the heavier elements and spreads those into space, the next generation of stars can collect a little bit of the heavy elements, and so they'll have a little bit more metals, what we call metals. And those would be called population 2 stars. And then the third generation, and our sun is supposed to be a third generation star, they would have the most metals. And the sun has quite a lot of metals for a star, and that would be called population 1. It's kind of backwards. Population 3 is the first generation, population 2 is the second, population 1 is the third. And we see population 1 and 2 stars all around us and in the distant universe. We've never seen a population 3 star. Interesting. But these farthest galaxies would have to be made, the earliest galaxies would have to be made of population 3 stars, because the heavy elements hadn't formed yet, right? Okay, so you got the secular predictions. Fewer galaxies at great distance. They should taper out because you're looking back in time. And there shouldn't be any beyond a redshift of 14 because that corresponds to a time of only 300 million years after the Big Bang. It's not enough time for galaxies to form according to the simulations. And the ones that you do see that are close to that distance ought to be irregular, low mass, baby galaxies, and they should have only population 3 stars. Now, it occurred to me, I want to make some predictions too, because I don't believe any of that nonsense. So I'm a biblical creationist, and so I don't necessarily believe you're looking back in time. That's a talk for another night. But in any case, I would expect to see lots of galaxies at great distances, even beyond redshift 14, because I don't believe in the Big Bang, and I don't believe galaxies formed. I believe they were spoken into existence by God, and I don't see any reason why he would stop at a redshift of 14. So I would expect there would be galaxies going way beyond that, and they'd have about the same density as nearby galaxies. Furthermore, since I don't believe that galaxies have evolved over billions of years, on account of I don't believe in the billions of years, I would expect that the farthest galaxies would be just like nearby galaxies, fully formed, massive, and well-structured galaxies, just like nearby. I don't believe in baby galaxies. Now, galaxies come in a range of sizes, right? There's dwarf galaxies and there's massive. Well, ours is pretty big. Ours is on the upper end. But I don't expect that looking farther out into space, you'd see smaller galaxies, because I don't think they've gained mass over billions of years, because I don't believe in the billions of years. Furthermore, I expect those farthest galaxies will have heavy elements, because I don't believe in a Big Bang that produced just hydrogen, helium, and lithium. I know from the Bible that the heavy elements were already around before the stars formed. How do I know that? Because in Genesis 1 and 2, God made the heaven and the earth. The earth was without form and void. Darkness was on the face of the deep. The Spirit of God was hovering over the water. H2O, O is oxygen. Oxygen existed on day 1. Stars are made on day 4. Which is first, oxygen or stars? Oxygen, yeah. So the heavy elements already existed. And so I don't see why there should be a generation of stars that didn't have any. So you can see why, how I'm motivated biblically to draw these conclusions. And you'll notice that these are basically the exact opposite of what the secularists were concluding, right? They think galaxies stop at redshift 14. I say they keep going. They think the farthest galaxies will be babies, low mass. I think they'll be high mass, well structured. They think the farthest galaxies will have no heavy elements. I think they will have heavy elements. The exact opposite. And because I have confidence in the Bible, I was confident enough that their predictions would be wrong and mine would be right, that I also tried to predict how the secularists would respond when their predictions fail. Okay? And you can read about this. I've got it online. This was my prediction. Secularists will respond to their failed predictions. They won't give up the Big Bang, because then they'd have to admit creation, right? So what they'll do is they'll just try to push the galaxy formation back even further. They'll say Webb discovers that galaxies formed much earlier than previously thought. Okay?
Painting yourself into a corner, so now galaxies have to form faster and faster and faster.
Yeah. So, but that's their problem. And you can read these predictions on the website, biblicalscienceinstitute.com. I wrote that January 21st, 2022. That was before James Webb had taken any data. It had just been launched, and I thought I better get on the ball and make these predictions before it actually observes anything. It wasn't until July of 2022 that we got the first data back of these distant galaxies. And so what did it find? Did it look out to a distance where you can see just only a few galaxies and then they kind of stop? This is what it saw. Yeah. Amazing. And again, you're not looking at a star field. Each one of those is a galaxy with hundreds of billions of stars each. They intentionally pointed it at a galaxy cluster. A galaxy cluster acts like a natural magnifying glass or telescope to what's beyond it, because it bends the light from those galaxies. Now that has the unfortunate consequence of causing some of these galaxies to look distorted. Like those, see how they're stretched out like that? In fact, some of these are the same galaxy. I think that one and that one are the same galaxy. It's just two different images. One's gone around, the light's gone around this nearby galaxy. One went one way, one went the other way, so you get two images. And there's multiple images of some of the galaxies in there, but it's really spectacular. But then far away from that, they look pretty normal. In fact, you see spiral galaxies here. And a lot of them are really red because they're getting close to the end of what James Webb can detect. So pretty amazing and beautiful and stunning and makes you want to worship the Lord. It really does. So in terms of the details, in terms of the quantitative details, what did they find? Lots of galaxies at great distances, even beyond redshift 14. They found galaxies at redshift 15, redshift 16, 17, some even out to 20. That is way beyond what the secularists were expecting. I was expecting that, but they weren't. So we got that one right.
Why did they think 14 would be the limit?
Because that corresponds to 300 million years after the Big Bang, and the simulations show that galaxies take longer than that to form. Yep. So, and then the farthest galaxies they found, fully formed, they didn't find baby galaxies. They found they're massive. Some of them are comparable of mass to nearby galaxies and well-structured. They found spiral galaxies out at those distances. They even found barred spiral galaxies, and those are supposed to take many billions of years to form. The barred spirals have, they have kind of that central bar, and then they start spiraling. They're beautiful. So they were amazed at the mass of these galaxies. They're comparable in mass to nearby galaxies. What about population 3 stars? Farthest galaxies have detectable heavy elements. They detected the signature of oxygen and carbon, things like that. The James Webb Space Telescope has a spectroscope on board. It can analyze the light, and by basically light gives off an atomic fingerprint. I've got some articles on the website if you want to see how that's done. But they detected this signature of heavy elements in these farthest galaxies. So how about that? So the creationist predictions were right, and the secularists were wrong. What about my prediction of how they would respond? I'm claiming, I predicted they'd say this: Webb discovers that galaxies formed much earlier than previously thought. Here's how they responded. Galaxies started forming much earlier than many astronomers previously thought. That's Yukon Today, August 9, 2022. Here's another one. Massive galaxies formed earlier in the universe than previously known. Nature News, July 27, 2022. Evidence is building that the first galaxies formed earlier than expected. Sky and Telescope, January 10, 2023. A lot of galaxies could have formed in the universe much earlier than previously thought. That's space.com, January 12, 2023. So pretty neat. I was waiting for one where they'd worded it exactly the same as my prediction. We got pretty close. So if you're keeping score, the secularists were predicting fewer galaxies at great distances and none beyond redshift 14. That's wrong. We were predicting that many galaxies at great distances exceeding redshift 14, and that's correct. Some out to redshift of 20 based on these, at least the preliminary findings. Secularists were expecting the farthest galaxies would be low mass and clumpy baby galaxies. That's wrong. We predicted that the farthest galaxies would be fully designed and mature. That's correct. We were seeing spiral and elliptical galaxies at these distances. The secularists were predicting the farthest galaxies would have only population 3 stars, no heavy elements. That's wrong. We were predicting that they would have heavy elements, population 1 and 2 stars. That's right. James Webb has confirmed that. So it's been a wonderful success. And 2022 was a very fun year to be a biblical creationist. It really was. Because we got to see these come in and watch the secularists squirm a little bit. That's always fun. So, well, it is. By the way, something else I want to point out too, because sometimes you'll say people, you have people, especially sometimes the flat earthers do this. They'll say, "Oh, NASA's making up all those images, and that's fake. It's all CGI." If NASA was faking all this, why would they constantly produce results that are embarrassing to them? That's what I want to know. Results that confirm biblical creation, right? And by the way, there are a lot of good Christians at NASA. So I got to take a tour of the NASA headquarters there in Houston by 2 astronauts who were Christians. It was very cool. So anyway, new research. There's some new stuff that you haven't heard yet, and you're going to hear it tonight. This will be published. It's already passed peer review. I don't discuss research before it's been peer reviewed, but now it's passed peer review, and it's going to be published in the Answers Research Journal. This was something that I looked into November, December last year. My speaking schedule was kind of light, so every now and then I get to do some actual research, and that's always fun. So what I did is I started looking at studies of the sizes, the angular sizes of these galaxies that we're seeing in the James Webb Space Telescope images. And this is the paper that will come out in a matter of weeks in the Answers Research Journal. So I'm going to give you a sneak preview of it. And what we've discovered here is really remarkable. It's really remarkable. So as you know, something that is close to you looks bigger than something that's farther away, right? In terms of its angular size. Angular size is how many fingers it would take to cover it up, right? So a car that's nearby looks a lot of angular size. A car that's up on a mountain, you could cover it up with your finger. The angular size is very small. The same is true of galaxies. Galaxies that are nearby tend to look larger, all other things being equal, than galaxies that are further away. Now, galaxies themselves come in a range of sizes, but if you could take a galaxy and move it farther away, it would look smaller. And I can kind of guess at the size of a galaxy. If I'm looking at it in my telescope, based on how big it is, I can tell you, oh, that's a relatively nearby one. If it's this big, that's a nearby galaxy. If it's a little puffball like that, it might be further away. So we'd expect that. That's just geometry, trigonometry. We understand that. Now, since the 1920s, since 1929, astronomers and physicists have figured that our universe is expanding based on the redshifts of these galaxies. And the assumption is that the fabric of space is actually expanding, and it sort of carries the galaxies along with it. And we'll talk more about the implications of that. But one implication of that is that this rule, where something looks smaller as it's farther away, only works out to a certain distance. And then stuff will start to look bigger again. Why is that? Well, I'm not going to get into the math of it because it's complicated, but basically it has to do with if the fabric of space is expanding, that acts like a kind of magnifying glass. And it turns out that the reverse, the smallest a galaxy should appear, occurs at a redshift of 1.6, where the light has been stretched out 1.6 times, okay? And beyond that distance, because of the stretching of the fabric of space, galaxies should start to look bigger again in terms of their angular size, how big they look in the telescope, okay? Now the thing about that, and I've known that for a long time, I learned that in grad school, and I thought, boy, that'll be fun to see. When James Webb goes up, you'll start to see farther galaxies looking bigger. We don't see that. We don't see that. And so I was a little bit surprised at that. I'm kind of shaking my head. The farther galaxies, and you can kind of estimate it based on their color, the way they've adjusted the color. The redder ones are generally more redshifted. That wouldn't have to be the case, but the way they've adjusted the colors, it is. And so, they look smaller. They look like they get smaller as they go further out. Granted, there's a range. That's weird. Why are we not seeing that magnification effect at a redshift of, and it's not very far out, it's 1.6. These galaxies go out, again, some of them go out to a redshift of 20. They ought to look really big, right? Weird. So, and this, again, goes back to the discovery of the Hubble law back in the 1920s. So what Hubble realized is that the farther away a galaxy is, the faster it's receding from us based on its redshift. And so what that means is the universe is getting bigger, which apparently it is. The assumption since the 1930s, actually even in the 1920s, the assumption is that the reason that galaxies are moving away from us and from each other is because the fabric of space is expanding. And that's something that Einstein's equations allow. Einstein discovered the equations that describe the relationship between mass and the fabric of space. And those equations allow for space itself to be stretched. We tend to think of space as nothing, but space is something. It has properties. It has properties, and apparently it can be stretched. And so the assumption was that as the universe is being stretched, the galaxies just kind of move along with it. It's like when you draw dots on a balloon. The dots are stationary, but if you blow up the balloon, they will move away from each other, not because they're moving relative to the surface of the balloon, but because the balloon is expanding. And so the four physicists who independently discovered that space could be stretched were Friedman, Lemaitre, Robertson, and Walker. And so the mathematics that describes this expansion is called the Friedman, Lemaitre, Robertson, Walker metric. Metric is the sort of how distances are described in space. And sometimes it's shortened to the Robertson-Walker metric after the latter two. So, but what I'm suggesting is, since that effect ought to make distant galaxies look bigger than they really are at distances beyond 1.6, and since we don't see that, what if the fabric of space is not expanding? Now, what if the galaxies are just moving away from each other, but space isn't? What if it's like that? Okay? Now, you need to understand, both of those would cause a redshift. And both of them would cause a Hubble law redshift, where the farther away a galaxy is, the more redshift it is. If space is expanding and the galaxies aren't moving, then the light, as it's traveling through that space, the space is being stretched, the light will get stretched. And the farther galaxies, the light's been traveling longer, so it'll be stretched more. So the farther away a galaxy is, the more its light's redshifted. But this will do the same thing, because if the galaxies are just moving through space, it'll be a Doppler shift. Those galaxies experience time dilation. Their clocks are slowed, and that will cause the frequency of light to be less, which means its wavelength is longer. And since the farther galaxies are moving faster, they'll be more redshifted. See? So they both cause the same result, a redshift. But you don't know which one's causing it. Is the redshift of a galaxy due to the fact that the light's moving through space and being stretched as it moves through space? Or was it already redshifted when it started because the galaxy is moving away from us? And space is not being stretched. So you can't tell just by looking at the redshift. They both generate the same effect. So the standard model on which the Big Bang is predicated assumes the Robertson-Walker metric. It assumes that space is expanding and the galaxies just go along for the ride. And by the way, most creationists, myself included, had assumed that that's right, because it's a natural explanation for why the galaxies are moving away. It matches the physics that Einstein predicted, or that he worked out. And so although the Big Bang requires that, this doesn't require the Big Bang. Most of us just assumed that God started the universe with size and has stretched it out since then, but we assume that he's stretching the fabric of space too, okay? We just don't think it started in the Big Bang. But now what I'm suggesting is we shouldn't have assumed that at all. Maybe we should have assumed that the galaxies are just Doppler shifted, and that's the reason for the Hubble law. Interesting, because if they're just Doppler shifted, you don't get that magnification effect. So that's what motivated me to do this, to think maybe space isn't expanding. Because if space is expanding, then galaxies beyond 1.6 should start to look bigger, beyond a redshift of 1.6. If space is not expanding, but the galaxies are just moving away from each other, you won't see that. They will continue to look smaller with distance, the equation's the same as you would compute in your high school trigonometry class. There's no weird magnification effect. So I thought, well, I wonder how the math works out and if it matches the observation. So I worked out the math and I computed the angular size of a galaxy. Now galaxies come in a range of sizes. So I said, let's pick kind of an average sized galaxy. And for our local group of galaxies, I went through and looked through all the sizes of them and averaged them. And a typical galaxy in our local group of galaxy is around 4,500 parsecs in diameter, 4,500 parsecs. And so I said, okay, let's take that galaxy, and how big would that galaxy look if it's at a redshift of 1, 2, 3, 4, 5, and so all the way out to 20. This is a semi-log plot, so they get closer together. One, right, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then they get even closer together all the way out to 20. And semi-log plots are nice because they allow you to compress a lot of space into a small graph. Anyway, the red curve is what you would get if the Friedmann-Lemaitre-Robertson-Walker metric is correct. If the fabric of space is expanding, that's how big that galaxy should look in terms of its angular diameter in arc seconds. And so at a redshift of 1, it's a little over 0.5, maybe 0.56 arc seconds, right? And you see it gets smaller until 1.6. At a redshift of 1.6, it's as small as it's going to look. And then beyond that distance, it should start to look bigger again and quite a bit larger as you get out to a redshift of 20. So that's the standard model. If space is not expanding, then I computed how big it should look as a function of redshift, assuming the redshifts are caused by the Doppler effect. That's the black line. So if space is not expanding, that 4.5 kiloparsec galaxy should look this big, and it just gets smaller and smaller and smaller as it gets further out. There's a third model I thought I'd play with too. It's called the tired light model. It was proposed by Zwicky a number of years ago. It's an alternative to the Big Bang. And in the tired light model, the universe is static and the galaxies aren't moving. But the reason for the redshift is that light, as it's moving, just kind of loses energy for some reason. And that would cause it to redshift. That model never really enjoyed a lot of popularity, but it had a couple of advocates over the last century. But it's being revisited because of the small size of these James Webb galaxies that we're seeing in the deep field. Okay? Now, the problem, of course, is that galaxies come in a range of sizes. They're not all 4.5 kiloparsecs. They come in a range of sizes. Nonetheless, so when we plot the actual values of these galaxies, the correct curve, half of the galaxies should be above it, half should be below, right? Does that make sense? Because if this is a typical galaxy, you'd expect about half of them would be bigger, about half of them would be smaller. So as we plot these different points, the points will scatter around the correct curve. And this has been done for galaxies that have been imaged by Hubble, and those will be over here because it can't go out as far. And then more recently, there have been some studies that have analyzed galaxies out here using James Webb Space Telescope data. And I want to show you the results of these studies. These are the angular sizes of galaxies from the Hubble spacecraft and then from the James Webb Space Telescope. Now, granted, there's a range, but remember, half of them should be above the correct curve, half should be below the correct curve. And you can see once we get out here, none of them are above the standard model. This is supposed to be a typical galaxy, but clearly typical galaxies are down here. Isn't that interesting? And so then it occurred to me, well, we need to compare apples with apples. These curves represent the size of an average galaxy. So what happens if I take these galaxies in a given redshift and average them down to one point? The point will represent the average of all of them, the median. In fact, here's what you get. Now, that is remarkable because in cosmology, rarely do the data fit the model as well as that. But again, the black dots here represent the average size of galaxies at that distance from various studies. The vertical bars indicate the standard deviation. That's kind of the range that you see there. And the points should be very close to the correct model, and they're all, three of them are directly on the Doppler model, what I'm calling the Doppler model. So that's compelling. So what does this mean? It means the fabric of space is not expanding. Galaxies are moving away from each other. The universe is expanding in that sense, but the fabric of space doesn't move with them. They're just Doppler shifted. The data are very consistent with that, remarkably consistent. And I'm using the results of other studies, very fine astronomers that have done this. In the previous plot, those are some of the studies that I looked at, where they've measured the angular size of these galaxies in James Webb Space Telescope data. So pretty neat.
Makes me think of Occam's razor.
Yeah, I think it's, yeah.
And it's far simpler than the...
It is. Yep. So that's what's compelling to me, is that the data fit very well this model. They don't fit the standard model at all. Now what that means, if you accept that explanation that the universe, the fabric of space is not expanding, it immediately eliminates a Big Bang. There cannot be a Big Bang. And you might say, well, wait a minute, the galaxies are still moving away from each other. Yeah. So if you run it back in time, do they all go back to a point? No, because they have some sideways velocities too. They will miss each other. In fact, some galaxies are blue shifted. You run those back in time, they just get further away anyway. Okay? So the galaxies do not all go back to a point. They would be closer in the past, but if you run it back far enough, they'll just miss each other and go back and re-expand the other way. In order to have the Big Bang, in order to have galaxies come from a point, you need the fabric of space to be a point, because then there's no getting away from the other galaxies because they're all at the same place. So this this is devastating to the Big Bang. That's what makes this so exciting for me. It's and frankly, it refutes an assumption that we've made for the last century, that the fabric of space is expanding. We've made that for the last 100 years, and apparently that's wrong. Isn't that fascinating? That opens up some new avenues for creation-based cosmological research. So I find that very exciting. I find it very exciting. Now, I have to discuss possible alternatives, because I have made an assumption. And I know how the secularists will respond. I could predict it this time just as well as I did last time. In fact, I will. And you can, I haven't written it up, but you can be my witness. Because I have made an assumption. I've taken a 4.5 kiloparsec galaxy, a galaxy that's 4,500 parsecs in diameter, and I've plotted its value at all these different distances. And I've said that's a typical galaxy. What I've done is I've assumed that the size of galaxies here is about the same as galaxies out there. Okay, I've assumed that. And we don't know that, because galaxies don't come with labels telling you their linear size. It would be cool if they did, but they don't. So what could secularists say? They could say, actually, the reason that these are all way down here is because galaxies out at that distance are really small. They'd have to be 5 to 10 times smaller in diameter than nearby galaxies. So if our galaxy is like that, they'd have to be like that. Okay, so that's what they're going to say. And so you might have even read in papers that we're surprised that these galaxies are so linearly small. They have such a small surface area. That's because they're assuming the red curve is correct, and they're miscalculating their true size. If you assume the black curve is correct, they're the same size as galaxies nearby. Okay. But what about that explanation? I think that's a bad explanation. I think that's a bad rescuing device for a couple of reasons. One, we already know from the light estimates, we've already estimated the mass of these galaxies. They're as massive as nearby galaxies. They have as many stars as nearby galaxies. So you'd have to argue that somehow these galaxies are just as massive as nearby galaxies, but compact for some reason, and somehow they just expand over billions of years. There's no mechanism that would cause that. It doesn't come out in any of the computer simulations. Apparently that just happens. That's not a very good explanation. The other thing, and it goes back to Occam's razor, it's not just that we have to explain the galaxies at this redshift. We have to explain them at all redshifts. The galaxies would not only have to be tiny at that distance, yet just as massive as nearby galaxies, but they would have to grow in exactly such a way as to make this curve look wrong and that curve look right. See, because they match the black curve at all distances. So that's what they're going to have to argue. They're going to have to argue that these galaxies are actually tiny, yet just as massive, and for some reason expand in just such a marvelous way as to make the standard model look wrong and the Doppler model look right. They could argue that. I can't disprove that.
You know how many galaxies were used at each point?
Well, each one of those is one galaxy. Yeah. Yeah, each one of those is one galaxy. So there you go. And there's a lot of scatter. These three galaxies are what form that bin. So, you know, that's why there is some variance. But I think it's absurd to think that galaxies somehow expand for no logical reason. It's in a way that's not predicted in any simulations without gaining mass, because they're already as massive as they should be. And we already know they have the right metallicities they should be. As far as we can tell, if the Doppler model's right, then there's no evidence of galaxy evolution at all. Galaxies that are far away are about the same as galaxies nearby in terms of we already know in terms of their brightness and mass. Even the secularists concede that. And in terms of their metallicity, the secularists concede that. Now we know that their angular size, their actual size, their linear size is the same as nearby galaxies if the Doppler model's right.
So that would fit in all other aspects that
Yeah.
created mature galaxies and then spread them out.
Right. So it's very consistent with creation.
It's not that we have, we created some people as, or Adam was an amoeba or whatever.
Yeah.
We're immature.
Right. The first humans, the first animals, the first plants made mature. The first galaxies also made mature. They didn't need time to grow. They certainly didn't need billions of years to grow. So pretty neat, pretty exciting. One other avenue of research I thought I would pick out, because there's one other difference too in terms of if the fabric of space is expanding versus if galaxies are simply moving through a non-expanding space. That creates a difference in the brightness of these galaxies. And the standard model in red, assuming that distant galaxies are about as bright as nearby galaxies, you'd expect to see that would be their computed, estimated actual brightness. It should be about the same. Whereas in the Doppler model, they should trend downward. That's the black line. And then the blue line is the actual fit to the data. So, and this is a little tricky because galaxies come in a range of brightnesses as well. So I just took the brightest galaxy in each bin, and you'd assume that would be sort of comparable. And then I took the least squares fit to those, least squares linear fit, and the blue line, the slope of that better matches the Doppler model than the standard model. So that indicates that not only are the angular sizes of these galaxies consistent with the Doppler model, but also with the brightness. The brightnesses are also consistent with what I'm calling the Doppler model. So I'm giving the name Doppler model to the idea that galaxies are moving through a non-expanding space. And that fits the data very well, fits the angular size data.
Shift value based on the spectrum. The red shift tells you the spectrum tells you the red shift.
Right, the spectrum tells you the redshift. Yeah. Okay. So what have we found? According to the Doppler model, the angular sizes of distant galaxies are consistent with their redshifts being caused entirely by the Doppler effect and not the Robertson-Walker metric, which describes the expansion of space. That's very exciting. It's brand new. It's brand new. The brightness of the distant galaxies is likewise consistent with the Doppler model and not the Robertson-Walker metric. It's not as conclusive there, I'll grant you. The curves are closer, but it's still closer to the Doppler model. There's no doubt. This suggests that no substantial galaxy evolution has occurred, which as a creationist is very satisfying to me. Because again, God created everything as an adult. He created galaxies fully functional. They didn't need time to get bigger. What's more, we don't see any evidence of evolution over distance, which suggests that distance does not mean time. Okay? So distant galaxies have approximately the same sizes and brightnesses of nearby galaxies. And whether you believe the Doppler model or not, we already know they have the same metallicity range in terms of heavy elements. They have the same mass as nearby galaxies and roughly the same luminosity as nearby galaxies. So those are already known, regardless of which model you like. So this means, the Big Bang cannot occur without an expanding metric. And so these James Webb Space Telescope data apparently disallow a Big Bang. So that's pretty exciting. You can't have a Big Bang without an expanding metric, and the data are not consistent with an expanding metric. So that's cool. The Doppler model, it's very consistent with ASK, if you've read my research on distant starlight. This is something I'm still analyzing, but the exact mathematics of this is very consistent with the light reaching us instantaneously. We're seeing the universe in real time. I'm not going to go into details on that tonight, but I do have follow-up research I want to do on that. So these two models dovetail, they go together. The Doppler model and ASK, they could be independent. One of them could be true and the other false, theoretically, but they work really well together. They work really well together. And so that paves the way for for further biblical cosmology models. And I think that's cool. I think that's cool. So this is just the beginning of some brand new research that I think is going to be revolutionary. So I do want to remind you of some of the resources we have out in the hall. We have Taking Back Astronomy. That's my kind of primer book on astronomy from a biblical perspective. We have a DVD that goes along with that, Astronomy Reveals Creation. Stargazer's Guide to the Night Sky, How to Better Enjoy the Night Sky from a biblical perspective. If you want to know about the next meteor shower or when's the next solar eclipse, you just missed it, right? So I went to Carbondale, Illinois to see that eclipse, and it was worth it. It was amazing. Your next one is in 2044, so good luck with that. Take your vitamins. Physics of Einstein, if you want to learn about time travel and distant starlight and things like that, it's all in there. Black holes, that's fun stuff. So it's a little techier than my other books, but it's high school level math really. So and I put the math in boxes because some people they get intimidated by the math. So you can skip the math and still get the ideas. But I wanted to include it because it's beautiful really. My brand new book, The Importance of Genesis, just came out, showing you how all Christian doctrines are predicated on the literal history recorded in Genesis. A very powerful resource and brand new. So we have that here tonight. I'd encourage you to pick that up. The Ultimate Proof of Creation, giving you a bulletproof argument for biblical creation. Very different from the kind of argument most people assume, but I think it's very powerful, and I think you'll enjoy that. And then do check us out on the web as well, biblicalscienceinstitute.com. So I'd be happy to take questions now, and the microphone is right there.
Yeah, we've got 2 microphones going. So Paul,
Okay.
if you will handle the front of the room, and I'll go back and catch the questions in the back. All right, who's going to be first here? Got a hand.
For those of us who are not familiar with ASC, is there some way you can give us an 8-second overview?
No. Maybe, I don't know. I'm still working on my elevator talk on that one, but it's hard because space and time are they're more complicated than people assume. Einstein discovered that. One of the things Einstein discovered is that the speed of light in one direction is not measurable. It is in fact something we stipulate, and therefore we have freedom in how we stipulate it, which is counterintuitive. It's counterintuitive, but it has to do with the fact that there's no universal now that is objectively agreed upon by all observers. So the bottom line is the speed of light can be different that way than this way. Now the round trip speed, the average speed, when we send light, bounce it off a mirror, bring it back, get the distance, measure the time, that's always 186,000 miles per second. That is set by God and cannot be changed. That's the round trip speed of light. That's unalterable. But the one-way speed, the speed in one direction, is a matter of convention, kind of like 12 inches in a foot. Why are there 12 inches in a foot? Because somebody decided there should be 12 inches in a foot, and we all agreed to it. So, because we didn't, I don't know, because we hadn't invented the metric system yet. So, but the one-way speed of light's like that. The one-way speed of light can actually be infinity when toward me, as long as it's half c when moving away from me. And people ask, what would cause that? It's not a question of what's causing it. We can either decide to make it the same in both directions or different. And I'm thinking the Bible uses an anisotropic. Anisotropic means different in different directions. Synchrony convention, whereby the speed of light is instant when moving toward me. All ancient cultures did that. So I don't think the Bible would be an exception to that. And that's the short answer. And then for the more detailed version, check out the website, biblicalscienceinstitute.com. Okay.
On the subject of dark matter and dark energy, it's my understanding, at least at this point, that there is no proof that anything like that actually exists. They're just assuming that it does for other reasons. But it kind of seems to me that if in fact that is real and it does exist, isn't that just their representation of God holding the whole universe together and causing what's going on with it?
Well, in some sense, everything is. I mean, gravity is the way God causes the planets to orbit the sun. Electromagnetic forces are the way God causes the atoms to hold together. So the fact that we can write down equations to describe these things tells us something about the mind of God, that he thinks mathematically about things, and that's for our benefit. But with dark matter, I think there's good reason to believe that dark matter exists. Yeah, and it's not based on any secular assumptions. It's based on the speed at which stars orbit the core of their galaxy. We can measure those speeds, and based on Newton's laws, we can determine the mass interior to that. The mass external to that doesn't really affect it. The mass interior does. And so we can, for stars at different distances, we can measure their Doppler effect that tells us how fast they're going. And then we can, from that, we can estimate how much mass is interior to that. And it's about 10 times more than what you would expect if the mass were merely stars and dust and gas. And so that tells us that most of the universe is stuff we don't even know what it exists. We don't even know what it is yet. But we know it's there because it exhibits a gravitational force on stuff that we can see. Dark matter is something that we can't see that exhibits a gravitational force on something we can see. So that's how we know it's there. And there are several independent lines of evidence that indicate that, yeah, there's a lot more mass than simply what we can see. And that includes the bending of the light by these galaxies. You can estimate the amount of mass that's in that galaxy, and it comes out 10 times more, very consistently, than the amount of stars that you can see. Now, dark energy is something different. Dark energy is a little more ethereal. It's something that the physics of Einstein allows for it, but it doesn't require it. And I will tell you that, let me back up to the graphs here. The Doppler model eliminates any need for dark energy. Now, that doesn't necessarily mean that there's not dark energy, but dark energy will not affect the angular sizes of these galaxies, whereas it does with this curve. If you change the dark energy, this curve will go up or down a little bit. But they can't move it too far because then it would be inconsistent with nearby galaxies. So the secularists need dark energy. We don't, and the Doppler model eliminates the need for it, but doesn't necessarily prove that it doesn't exist. It just makes it irrelevant.
Excellent. Actually, you're on the exact plot I wanted to talk about. I'm curious, the deep fields you showed, lots of galaxies. I know this is based on preliminary data. I'm curious how much more data you expect, twice, 10 times more, to maybe tighten up these error bars as time goes on?
At least 10 times, hundreds of times. There was another data set that I considered including, and it already had as much data as all these guys combined, and it was kind of in this range, and I would have loved to have included it. But the problem is they were looking a little too close to the area where the galaxies have been gravitationally lensed, which makes their sizes artificially large. And so I felt that those data were biased. Now, they admitted that they did that, and they said, we haven't compensated for that yet. They said, we're going to. But that's an added complication that makes those data unreliable as is. So I only used these guys because they were looking at different deep fields that are not gravitationally lensed, or in the field I showed you where they're farther enough away that the size of the galaxy would not be affected. So, but there's a lot more data coming. Oh yeah, a lot more coming. And I think it'll tighten up, those dots. I think they'll fall right along the line.
Is the data available as public domain?
Is the data available as public domain? Yes. Yeah. Your taxes have paid for this. So yeah, you can find it. Now, the raw data is available easily. Now, with these guys, I found these, so you can too, right? And I didn't need any special access. I think one of them I had to use a graph that he had used, but the rest of them I found their data online. It's a little tricky, but you can find it. You can find where they have released their data, their results to the public as well. And I'm very grateful for that.
Okay, can we be sure we're using the mic up there?
Okay. All right. So, Dr. I think I heard you say the James Webb Space Telescope findings disallow the Big Bang. I mean, that has to be such a punch in the gut, kind of like finding the soft tissue of a dinosaur. I mean, what are they going to do? I mean, what?
Yeah.
How do we follow this? Because you said this was pretty new, just finally got out of peer review. Where do we, how do we follow that?
Yeah. Well, this article will appear in the Answers Research Journal in a few weeks. Andrew, it's already they're just formatting it now. It's already past peer review. It's ready to go. I can tell you what they're responsibly. They'll say that these galaxies just happen to line along that curve. It's a coincidence because galaxies at that distance are actually 5 to 10 times smaller than nearby galaxies. They must expand by some mechanism that we haven't yet discovered. And I'll point out they'd have to do it to match that line at all redshifts. And I don't think they're going to have a good answer to that. But that's their only option. And so that's where they're going to go.
Okay, let's take one from back here. Hang on.
Oh, thank you.
Are you ready for the Galileo treatment?
I'm a creationist. Bring it on.
So how come those plot lines don't start at the same place?
If I would, well, it starts at a redshift of 1. If I'd run it all the way back to 0, they would all match. Out to a redshift of 1, they're all pretty similar. But yeah,
because I can't read it from here. So.
Oh yeah. It's because I started it at 1 because we don't have good clean data for galaxies that are much closer than that because there's an effect that kicks in called the Malmquist bias, and I didn't want to have to deal with that. It's just it would create artifacts.
Enough said. Thank you.
Yeah. Yep.
And you talk about space as though there's fabric or some substance or something. Mm-hmm. It's almost like something has to be in space to call it space. Otherwise, to me, there's just emptiness. So, I mean, what's going on in the minds of astronomers over emptiness?
Okay. Well, space it's not nothing. It has properties. For one, it has dimensionality. It's three-dimensional. You can put 3 perpendicular lines, perpendicular to each other, through a point in space, but not anymore because space has 3 dimensions, right? So it's three-dimensional. It has that property. It has some properties that allow electric fields to propagate through it. So it has what's called an electromagnetic permittivity and permeability. empty space we're talking about. Now, substances have those properties too, and they're different in substances. But empty space has an electromagnetic permittivity and permeability. And so that's why waves can travel through space. Because they used to say, how does that happen? How does light travel through space? And yet they said there was this invisible ether that's filling space. Well, we don't really need that if space itself has properties that will permit a magnetic field and an electric field. So it's a little abstract to us. We've all been trained to think, if you've gone through a public school system, you've been trained to think as a materialist, that everything that exists is matter and energy. And we need to open our minds and recognize, well, God's not matter and energy. He certainly exists. He's more real than anything in his creation. So space is real. It exists and it has properties. And apparently one of them is that it can be stretched. But apparently it's not.
With your peer review, have you heard, what kind of feedback did you get? It seems like that would have started some rumblings within the community because of the...
Yeah, and I submitted it to a creationist peer-reviewed journal, Answers Research Journal. So
it hasn't
2 out of
hit
3.
the outside.
No, but you know what? I'm fairly confident there won't be a lot of objections to it. I'm using data that other secularists have published. I mean, these are not, to my knowledge, creationists. I'm using their data. All I did was the math, and I showed in the paper how to do the math, so they can, if they think I did something wrong, they can tell me. But I don't think they will. The red equation, it's found in any standard cosmology textbook. And the black one's easier because that's just high school trigonometry to do that one. Because if the space isn't expanding, then geometry behaves as normal. So I don't think they're going to have any problem with my method. They'll say my conclusion's wrong because they'll say those galaxies are actually tiny.
Okay,
That's the only thing they can do.
Sorry, we've got a question back here.
If the blanket of space keeps getting bigger, will it keep getting bigger forever? And could it possibly get smaller? Like, could the galaxies get closer back together?
Okay, that's a good question. We think that galaxies have enough energy that they will continue to go out forever. So they'll never turn around. Now, there's some galaxies that are already kind of moving toward us, like the Andromeda Galaxy, and that'll move toward our galaxy. But the other galaxies will continue to expand forever. So we don't think they're going to turn around. They have too much kinetic energy to be stopped by their mutual gravitational influence. And that's true whether the fabric of space expands or not.
I'm going to ask kindergarten questions.
Yeah.
Hopefully there's others that might be in this room because I'm very much a novice. So 3 questions because I'm going to only get the mic once. Okay, a funny, perhaps question, 3 parts. Aliens, if you guys talk about that, because you see on TV these supposed intel whistleblowers, giving testimony. Other life-supporting planets, if so? And then what about the U.S. federal government intel groups? Are they involved in data control of the Webb information? Okay. And I'm not really quite understanding, if you could put it in really simple lay terms, how, if you are saying this, that the expanding galaxies theory refutes the Big Bang.
Okay, that's 4 questions. Let's try to.
I'm a retired attorney, so.
We'll see. That's good. That's good. Okay. I don't think there's aliens. I don't think there's extraterrestrial life out in space. God formed the earth to be inhabited, Isaiah 45:18. Earth seems to be specially designed for life. Most of the universe is hostile toward life. It's not. We have this island, this amazing island here on Earth that's designed. It's got all the right features for life. And the Bible does seem to single out Earth as being unique in that. It doesn't say there's not ETs, so I'll grant you that. But I would be astonished if we found intelligent life out in space, especially intelligent life, because if you got Vulcans and Klingons out there, you got some theological problems because they can't be saved because they're not related to Christ. It's because we're related to Christ that his blood counts for us on the cross. He's our kinsman redeemer. But Lieutenant Worf is out of luck because he's a Klingon. He can't, he's not related to Jesus, so he can't be saved. Lots of theological issues. I'm not persuaded. I know there are these reports and things like that. I'm just not persuaded by them. Planets that are potentially habitable, we haven't found any. We found a few planets, very few, that are about the size of the Earth. And they'll say, here you go, an Earth-like planet. What they mean is it's about the size of the Earth. And next time you hear that, take a look at Venus. Venus is the same size as the Earth. And it has a surface temperature of 900 degrees Fahrenheit, an atmosphere of toxic sulfur dioxide and and sulfuric acid and things like that. Atmospheric pressure is 100 times that of the Earth. It would crush you like a tin can. So when we find these other planets, my expectations are going to be more like Venus, but we can't see any of them close up anyway. I forget your question number 3. Yeah, well, I know they do some of that because it's happened in the last few years. I've seen it. I've seen certain things that have been suppressed, but they can't control. They can't control it all. There's still a lot that gets through. So I'm not sure how much of that happens. I'm sure it happens, but I'm not sure how much of that happens.
With the Webb.
Yeah.
Okay.
You're talking about the Webb Space Telescope.
Yeah, right. Because
I don't think so. NASA is really good about being open with their data. I've been very impressed with that. So
Different than Hubble? Isn't that very different than what we've seen in the past? The Webb is available.
yeah, well, yeah,
It seemed like you had to work for NASA or one of the contractors to get access to the.
Okay, could we please use the mic because we can't hear the questions back here.
yeah. He's asking about access to data and whether or not it's harder with Hubble. I don't think so. I mean, the data are available, and there's different avenues you can do that, and there's different platforms you can do it. And I've looked at some of the platforms for the James Webb Space Telescope, and some of them are, they're written by people who know how they work, and they don't write good instruction manuals.
Right.
So it's hard to access the data sometimes. But both Hubble data and James Webb are freely available because they've already been paid for by your tax dollars.
yeah.
So they are available. But it's just sometimes the interface is not as good as it should be. And I've experienced that with some of these. I'm like, man, anybody could have written this better. Oh. And then and then
the expanding universe
yeah.
supports the
So
repeats the Big Bang.
yeah, so in order for the Big Bang to happen, the fabric of space has to be expanding. In which case, the galaxies should lie along this curve. But they don't. They lie along this curve. And that suggests that the fabric of space is not expanding. The galaxies are moving through it. So the universe is getting bigger in terms of the galaxies moving through it. But the fabric of space doesn't expand. And that eliminates the Big Bang, because the Big Bang requires that space all go back to a point. And space can't go back to a point if it's static.
Okay, I have a two-part question. The first is, if galaxies are moving through space and not with it, can we assume that space expands infinitely? And if it doesn't, what would happen if the galaxies reached the end of space?
Okay. Yeah, I don't think there's like a wall or anything out there. I mean, it's a good question. We don't really know the answer to that. But if the Hubble law apply, I'm assuming that the Hubble law is proportional to velocity at all distances, and that fits the data really well. Now, whether it won't when you get farther out, I don't know. But so far, I mean, that's an incredible redshift of 20, and it still fits the data perfectly. That's amazing. So I'm inclined to think it's linear on out. What does that mean? It means there's a maximum distance. It's weird. It means there's a maximum distance to the farthest. There's not necessarily a farthest galaxy, but there's a farthest distance at which a galaxy can be found. And it's about 13.8 billion light years, something like that. It's the inverse of the Hubble constant. And the reason for that is the galaxies have a speed limit. They're getting faster and faster and faster until they get to the speed of light, which means there's a maximum distance. But the weird thing is, there could still be, even though there's a finite distance at which the last galaxy could be found, there could still be an infinite number of galaxies in the universe. And that's strange, but it's because of length contraction. These galaxies that are moving away at high speeds, their length is contracted relative to us, which means you can pack more galaxies in that space, more and more galaxies. Now, from their point of view, they would not be contracted. We would be contracted, and they would look perfectly normal. So they could see a galaxy that's 13.8 billion light years away. It's a weird effect. And I haven't explored all of that yet because this is new. This is a brand new model, and it's very different from the expanding space idea. So, yeah.
Okay, so you were saying that when Hubble was launched, they were working on James Webb in advance. So is there another James Webb version 2 being worked on, thought of, or is this it?
I'm sure there is, but I'm not privy to it. I'm sure there is. They're always thinking of the next project.
Okay, I think we've got time for maybe one more question, and then we're going to have to cut it off.
Okay, my question is 4-part.
quick ones though, simple. What is the temperature of deep space? I would think it would have been pretty close to the
It's
absolute.
it's pretty close. It's 2.7 degrees above absolute zero.
So why do they need all of that protection around the James Webb?
Because it's in the solar system, and the solar system has this really bright light bulb right at the middle of it, the sun.
So
it's for the
if
sun.
Further out, they wouldn't need that.
True, but you'd have to get way far away. So yeah.
Second, does the red shift all around us mean we're in the center of the universe?
It's a good question. The answer is no, because all other galaxies presumably would see the same thing. They would say, oh, I must be in the center because everything's moving away from me. And another guy over here says, no, I'm in the center because everything's moving away from me. Well, if everything's moving away from each other, then there is no unique center.
Okay. How far away is heaven?
Well, in terms of the realm of God, the kingdom of God is among you, in your midst, right? Right?
And how could heavenly beings move at speeds faster than light to minister throughout the universe?
Well, I don't know that they do. I don't know that they don't. Okay. But we're talking about spiritual beings, so they're not necessarily made of atoms and things like that.
All right.
So I do think angels experience time. I think there's some evidence of that in Scripture. The angel that was dispatched to answer Daniel was delayed for some time. So they seem to experience time. Whether they experience the spatial dimensions the way we do, I don't think that's known. Now God can give a temporary body to an angel. We've seen him do that. But that seems to be a rare occurrence and something that is by God's divine decree and for a period of time.
The last part is if we're saving up our pennies for one of your books, what would you recommend for kind of an entry level first book?
My latest book, I always think the latest thing I write's just the best. So. But it's called The Importance of Genesis. And I genuinely think it's probably the most important book I've written, because it shows you why the history in Genesis matters and why it has to be the literal history. Otherwise, Christian doctrines crumble. That's why we're seeing these problems we have in our nation. Our nation's rejected the Bible, and they've started in Genesis. Claiming millions of years of evolution undermines the gospel at the very first verse.
Thank you.
Sure.